Hello ladies and gentlemen. In the fourth tutorial on the series on the Parallel Axis Theorem, we want to show you how to calculate the product of inertia of composite areas. Remember that composite areas are somewhat complex areas that are composed of multiple simple areas. The equation for the product of inertia of composite area is analogous to the one for the area moment of inertia of a composite area. This means that you need to add together the individual products of inertia of the partial areas with respect to the reference coordinate system y prime, z prime, whereby the parallel axis theorem is applied to each partial area. So, without further ado, let's begin the calculation of the product of inertia of this L-shaped body. As you can see, this body is composed of two rectangles. One rectangle in panorama format and the other rectangle in portrait format. For better reference, let me label the rectangles as A1 and A2. As we did with the area moment of inertia of composite areas in another video, we're going to consider each rectangle separately and carry out the mathematics individually before adding together the partial products of inertia. Starting with the first rectangle, A1, I sub yz is the product of inertia with respect to a centroidal coordinate system. And if your body is such that at least one axis is an axis of symmetry, the value of I sub yz automatically becomes 0, as you've learned in the text and in another video on products of inertia. Therefore, I sub yz is going to be 0. And let me write down I sub y prime z prime. That is the product of inertia with respect to the y prime z prime axis of the area A1 for the upper rectangle. I sub yz, as I mentioned, is 0, and y sub cg prime, that is the y prime distance between the origin of the reference coordinate system and the centroid of area A1. So the distance between this point and the centroid along the y prime axis. And if you look closely, that distance is negative b half. The centroid is located at b half, and since that distance is in the negative y prime region, the value is therefore negative. I'm going to open up a bracket and write down minus b half z sub cg prime, that is the z prime distance between the origin of the coordinate of the reference coordinate system and the centroid. And that distance is positive a half times a half. And capital A, that is the area of the rectangle. And that is A times B. And the value of the product of inertia of rectangle 1 is ultimately 1/4 times a squared times b squared. So that is your partial product of inertia for the rectangle A1. And now we need to compute the product of inertia for the rectangle A2. And here, you need to check closely what is the distance between the reference coordinate system and the centroid of rectangle 2. And unlike with area moments of inertia, the sign, the algebraic sign of the distance matters for the product of inertia. Since the rectangle is symmetric around both the y and z axis, the value of y sub yz is going to be 0, as it was the case for the rectangle A1. And then minus, what is y sub cg prime? Let's see. The origin of the reference coordinate system is here, and the y prime distance between that origin and the centroid of area 2 is this distance, the one that I'm showing with the hand. And in mathematical terms, that distance is b half plus a half. Sorry, it's actually minus. Let me just. It's minus b half plus a half. Now, if you don't consider the negative sign, if you simply look at the absolute value of the distance, it's going to be b half plus a half, but since that whole distance is in the negative y prime region, b half plus a half must be affixed a negative sign. Let me get the plus more precise. So b half plus a half, and the whole thing affixed with the minus, and z sub cg prime, that's the z prime distance between the origin of the reference coordinate system and the centroid of A2, and that distance is a plus b half. And that's positive a plus b half. And then don't forget to multiply by the area a times b. And the result of that equation is minus 3/4 a squared b squared minus 1/4 a times b to the third power minus 1/2 a to the third power times b. And since negative times negative is positive, that term will become positive altogether. And finally, we have to add the partial products of inertia together to obtain the total product of inertia. Adding them together only requires us to add 1/4 a squared b squared to this term. And all you have to do is to add 1/4 a squared b squared to 3/4 a squared b squared, and 1/4 plus 3/4 is gonna be just 1. So I sub y prime z prime is equal to I sub y prime z prime of a1 plus the product of inertia for area 2 and that is equal to a squared b squared plus 1/4 a times b to the 3rd power plus 1/2 a to the 3rd power times b. In conclusion, whether you calculate the product of inertia using the parallel axis theorem for simple areas or composite areas, it is always important to verify that the algebraic sign of y prime or z prime is correct, and you can do so by checking whether the distance extends in the positive or in the negative region of the respective axis. We hope that you liked this video and that it was helpful for your course. Goodbye and good luck.